Deploying one container is easy. But what happens when you need to deploy hundreds of containers across dozens of servers, keep them running, replace them when they crash, scale them up during traffic spikes, and roll out updates without any downtime? That's an entirely different problem. And that's exactly the problem Kubernetes solves. In the next 10 minutes, I'll show you how Kubernetes works, from the ground up. Let's start with the problem. Imagine you have a web application running in Docker containers. In development, you run a few containers on your laptop. Easy. But in production, things get complicated fast. You need to run containers across multiple servers for reliability. If a server dies, the containers on it need to restart somewhere else. During a flash sale, you need to spin up 50 more copies of your checkout service in seconds. You need to update your app without taking it offline. And you need load balancing, service discovery, secret management, and storage orchestration. Managing all of this manually is impossible at scale. You need an automated system, an orchestrator, that handles all of this for you. That's what Kubernetes is. Kubernetes, often shortened to Kubernetes, is an open-source container orchestration platform originally designed by Google. Google had been running containers internally for over 15 years using a system called Borg. In 2014, they open-sourced the ideas behind Borg as Kubernetes, and it quickly became the industry standard. So what does orchestration actually mean? Think of Kubernetes like a conductor of an orchestra. You have dozens of musicians, those are your containers. The conductor doesn't play any instruments. Instead, they coordinate everyone when to start, when to stop, how loud to play, how to stay in sync. Kubernetes does the same thing for your containers. You tell Kubernetes your desired state, I want 5 copies of my web server running, and Kubernetes makes it happen. If a container crashes, Kubernetes replaces it. If a server goes down, Kubernetes reschedules those containers on the healthy servers. You declare what you want, and Kubernetes figures out how to make it real. Let's look at how Kubernetes is structured. A Kubernetes cluster has 2 main parts, the control plane and the worker nodes. The control plane is the brain of the cluster. It has 4 key components. The API server is the front door, every command you run goes through it. ect is the cluster's database, it stores the entire state of your cluster as key-value pairs. The scheduler watches for new pods that don't have a node assigned and picks the best node to run them on. And the controller manager runs a set of controllers that constantly check whether the actual state of the cluster matches the desired state. If you asked for 5 replicas and only 3 are running, the controller creates 2 more. Worker nodes are where your containers actually run. Each node has a kubelet, an agent that talks to the control plane and manages the containers on that node. It also has kubeproxy, which handles networking rules so your containers can communicate. And it has a container runtime, usually containered, which actually runs the containers. The control plane makes decisions, the worker nodes execute them. In Kubernetes, you don't deploy containers directly. Instead, you deploy pods. A pod is the smallest deployable unit in Kubernetes, and it's a wrapper around 1 or more containers. Most of the time, a pod runs a single container, your application. But sometimes you need a helper container alongside it, for example, a sidecar that handles logging or a proxy that manages network traffic. Those containers share the same network namespace, meaning they can talk to each other on localhost, and they share the same storage volumes. Why not just use containers directly? Because Kubernetes needs a higher-level abstraction to manage scheduling, networking, and lifecycle. The pod is that abstraction. Pods are ephemeral, they can be created, destroyed, and replaced at any time. You should never think of a pod as a permanent thing. Kubernetes treats them as disposable units, and that's actually a feature, not a bug. It enables self-healing and scaling. In Kubernetes, you don't manage individual pods. Instead, you use deployments. A deployment tells Kubernetes, I want 3 replicas of my web server, using this container image, with these resource limits. Kubernetes creates a replica set under the hood, and the replica set ensures exactly 3 pods are always running. If a pod crashes, the replica set detects it and creates a new one. If you scale up to 10 replicas, the replica set creates 7 more pods. Deployments also handle rolling updates beautifully. When you push a new version of your app, the deployment gradually replaces old pods with new ones, 1 or 2 at a time. At every step, it checks that the new pods are healthy before continuing. If something goes wrong, you can roll back to the previous version with a single command. This means zero downtime deployments become the default, not the exception. You declare what you want, Kubernetes handles the how. Pods are ephemeral, they get new IP addresses every time they're recreated. So how do other pods find them? This is where services come in. A service provides a stable network endpoint for a set of pods. It has a fixed IP address and DNS name that never changes, even as the pods behind it come and go. Kubernetes has several service types. A cluster IP service is the default, it's only accessible inside the cluster. Other pods can reach it by name, like http://myservice. A node port service exposes the application on a static port on every node in the cluster, so external traffic can reach it. A load balancer service integrates with your cloud provider to provision an actual load balancer, an AWS ELB or a Google Cloud load balancer that routes traffic to your pods. And an ingress is not technically a service, but it's how you handle HTTP routing. An ingress controller lets you define rules like requests to api.example.com go to the API service, and requests to app.example.com go to the front-end service. All of this happens through simple YAML declarations. Applications need configuration, database URLs, API keys, feature flags. Hard-coding these into your container image is a bad practice because you'd need a different image for every environment. Kubernetes solves this with ConfigMaps and Secrets. A config map stores non-sensitive configuration as key-value pairs. You can mount it as environment variables in your pod, or as a file on the containers file system. When you update a config map, pods that mount it as a volume automatically pick up the changes. Secrets work the same way but are designed for sensitive data, passwords, tokens, certificates. Secrets are base 64 encoded and can be encrypted at rest in ect. You reference them in your pod spec just like config maps. This separation of configuration from code is a fundamental Kubernetes principle. Your container image stays the same across all environments. Only the config maps and secrets change. This makes your deployments reproducible and your secrets manageable. Pods are ephemeral, so where does persistent data go? Kubernetes has a storage abstraction built around persistent volumes. A persistent volume, or PV, represents a piece of storage in the cluster. It could be a cloud disk, an NFS share, or local storage. A persistent volume claim, or PVC, is how a pod requests storage. The pod says, I need 10 gigabytes of fast storage, and Kubernetes finds a matching PV or dynamically provisions one through a storage class. Storage classes let you define different tiers of storage, fast backed by SSDs, standard backed by spinning disks, replicated for high availability. When a pod references a PVC, the storage is mounted into the container. Even if the pod is destroyed and recreated on a different node, the same volume gets reattached. This is critical for stateful applications like databases. Kubernetes uses stateful sets instead of deployments for these workloads, which provide stable network identities and ordered startup and shutdown. Let's see how everything fits together when you deploy an application. You write a YAML manifest that describes your deployment, service, and any config maps or volumes you need. Then you run kubectl apply. Here's what happens behind the scenes. The kubectl command sends your manifest to the API server. The API server validates it and stores the desired state in ect. The deployment controller notices a new deployment and creates a replica set. The replica set controller sees that 0 pods exist but 3 are desired, so it creates 3 pod objects. The scheduler sees 3 unscheduled pods and assigns each to a worker node based on available resources, affinity rules, and constraints. The kubelet on each assigned node pulls the container image, creates the container, and starts it. The service controller sets up the networking so traffic reaches your pods. This entire process typically takes just a few seconds. And from that point on, Kubernetes continuously monitors the actual state and reconciles it with your desired state. This is called the reconciliation loop, and it's the core design pattern of Kubernetes. Let's see how Kubernetes works in a real production environment. A typical setup uses namespaces to isolate teams and applications. The frontend team deploys to the frontend namespace, the payments team deploys to payments, and so on. Each namespace can have its own resource quotas and access policies. For continuous deployment, teams push code to Git, which triggers a CI pipeline. The pipeline builds a new container image, pushes it to a registry, and updates the Kubernetes deployment manifest. Kubernetes then performs a rolling update automatically. For observability, teams deploy monitoring stacks like Prometheus and Grafana inside the cluster to track metrics. They use the horizontal pod autoscaler to automatically scale services based on CPU usage or custom metrics. During a traffic spike, Kubernetes adds more pods. When traffic drops, it removes them. Companies like Spotify, Airbnb, and the New York Times run their production workloads on Kubernetes. The ecosystem around it, Helm for package management, Istio for service mesh, Argo CD for GitOps, makes it incredibly powerful for building cloud-native applications. Let's recap what we've covered. Kubernetes orchestrates containers across clusters of machines. The control plane manages state, while worker nodes run the containers. Pods are the smallest deployable unit. Deployments manage replicas and rolling updates. Services provide stable networking. ConfigMaps and Secrets separate configuration from code. Persistent volumes handle stateful storage. And kubectl apply kicks off a reconciliation loop that continuously maintains your desired state. If you want to go deeper, check out our upcoming videos on Helm, Kubernetes networking deep dive, and building a CI/CD pipeline with Argo CD. If you found this helpful, hit that subscribe button. Thanks for watching.